Okay, so you have to be able to name a hexose. What does hex mean? 6. So hexose example you should know is glucose. Glucose has 6 carbons. The next one you have to be able to name is pentose. Pent means 5. 5 carbon sugar example is ribose. And the last one you have to be able to name is a 3 carbon sugar. A 3 carbon sugar, triose. The example is glyceraldehyde. Do you guys recognize that?
Yeah.
Remember phosphoglyceraldehyde from cell respiration, PGAL.
Yeah, that's right.
That's awesome.
Yeah, it is.
All right, so there is another 3 carbon molecule that we're going to learn later, but it's a lipid, and its name is glycerol, so we don't want to get those mixed up. This is the 3 carbon glyceraldehyde. Phosphoglyceraldehyde is very similar to this, only it has phosphate group, right? All right, so keep moving. I put this picture here because I didn't know if it would confuse anybody. Last block when we were talking about functional groups, and I showed you glucose, and I had it as an aldehyde, and then I showed you fructose, and I had it as a ketone. They were both in linear structures. Did anybody notice that? They were like in a line instead of in a ring. So 90% of the time you see it on a test or in a worksheet or whatever, it's going to be, glucose is going to be in a ring structure. That's because when you put glucose in a solution, it forms a ring. So the linear structure you wouldn't find, for example, in a cell, because the cell is made up mostly water, and so it forms the ring structures. You don't have to be able to draw the linear structure. You are going to have to be able to draw the ring structure, so we're going to talk about how to do that. This part here with the number, I'm going to skip it for now. It's not really for today. Talk about it more when we do DNA and stuff like that. So we have 3 different kinds of sugars. Monosaccharides, what does mono mean? 1. Disaccharides, 2. And polysaccharides, many. We do have something also called oligosaccharides, which is greater than a disaccharide, but not.
Teachers, please lock your doors and send all starting students to the elevator. Thank you.
Polysaccharides are really large molecules, so we have some that are in between. You might see the word oligosaccharide, which means it's bigger than a disaccharide, but it's not a really large sugar like a polysaccharide. So examples of monosaccharide? Glucose. Who else? Fructose. Nah, sucrose is a disaccharide. Galactose. Ribose. Good. Disaccharides. Sucrose. Lactose. Anybody go to Steak and Shake? Ever get a chocolate? Maltose. So we got sucrose, lactose, and maltose for disaccharide examples. And then polysaccharides, what are the 3 I told you have to know? Cellulose, glycogen, and what's the one? Plant storage. Starch. Good job. Huh? Glucose, ribose, fructose, and galactose. There were actually 4. More on those in a minute. So let's look at how we make a disaccharide or a polysaccharide. Do you guys see, I'm going to use my little pen here so the people watching online can see it. Do you guys see that this is 1 glucose here? Oh, you can't see that. Psych. Now can you see it? Hey. 1 glucose right there. The next glucose is right here. There we go. Oh, it looks like eyeballs. Okay. If we want to put two glucose molecules together, what has to happen is both of their OH groups right here, and right here you guys see both H's? Okay? They have to be facing the same direction. In this case, they're both facing down like this, and they can interact with each other. You put two H's together, you can take out a water right here. And it marries them. Look, the ring is left. That ring is representing eternal marriage. Unless water comes along again. Then it's a divorce. Okay, so this reaction is called dehydration synthesis. What's the other name for it? Condensation. So we have two hydroxyl groups facing the same direction from two different glucose molecules coming together. H2O comes out, and they're left with an O bonded between them. Questions on that? By the way, if I put glucose and glucose together, what do I make? Maltose. And do you guys remember learning about a peptide bond? Where do you find peptide bonds? In proteins. So I don't know why, but in 9th grade they don't teach anything other than the peptide bond, which is kind of odd, but whatever. In sugars, when we do this reaction with a sugar, we create what's called a glycosidic linkage or a glycosidic bond. So they have their own kind of bond. Here's another example. This is glucose over here. This has 1, 2, 3, 4, 5, 6 carbons. Did you guys know that everywhere there's a point, there's a carbon? Did you guys know that? Okay. Everywhere there's a point in the drawing of the circle, there's a carbon. They don't write them all in because I guess that would be too busy. But there's a carbon here. There's a carbon here. Everybody's good? Okay. So this has 1, 2, 3, 4, 5 carbons. And then there's a 6th one right here. So this has 6 carbons. But it doesn't look the same as glucose. Can you see the difference? That's glucose right here. Who is this guy that also has 6 carbons? That's fructose. So glucose and fructose, my hydroxyl groups are still facing the same direction, so I can still combine them by removing a water. This is kind of strange if you guys think about it. You took a glucose and a fructose, and you put them together, and out came water. That's not strange to anybody? Like, I made water by putting 2 sugars together, right? It's a weird thing to me. I don't know why. But glucose and fructose make sucrose, and sucrose is another word for table sugar. By the way, too much sugar is bad for your health. It causes diabetes. What if they're already together, like this sucrose guy? If they're already together, can I break that glycosidic bond? Yes, just the opposite way that I made it. So now I must add water, right? And the H2O forms, again, splitting it up. Okay. Let me see if I can... Do you guys... I'm going to try to do this on here instead of on the... paint. What I'm going to show you is the same thing on your slides, but I think it makes more sense if I try to show it from here. So I'm going to draw a glucose molecule for you, okay? And it's not going to look too awesome, but you'll get the hang of it. What? There we go. Okay. Can you see this has 1, 2, 3, 4, 5, 6 sides and one little carbon sticking up? And that, my friends, is a glucose. They're easy to draw because they look like really, 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 really fat cats. See the little head right there? And he's so round, he doesn't even have legs, but he's got his tail sticking up. Okay. Now, the first carbon here has a hydrogen, and it has an OH group, a hydroxyl group. And that happens to be on all the carbons. Do you guys see it in your picture? This one. Down. OH. H. Except this one, which just has an H. And this one will be up. OH. You got to be able to draw this. Listen, if I can draw it, you can draw it. And then this will be CH2. OH. Is that good?
Yeah.
All right, I want to connect it to another one. Oi. Listen, I'm not going to draw all of them. I'm just going to draw this one. Okay. Is that okay? But on this side, I'm going to put the OH up here. Pretend you didn't notice that. Okay, all the others are the same. Do I have to draw them all in? Okay, pretend like they're all the same. Can I connect these two glucoses? Wait, why not? These are facing the same direction. Look. Both OHs are facing down. Can I not take out a H, 2, O, and it will leave this O here and they'll be married? Yes.
Oh, so it doesn't matter which way it faces?
Well, it does, but in this case they're both facing down. That's okay, right?
Oh, okay, so it's the arms that have to be facing down. It's not the hydroxyl group at the end that has to be rearranged.
Hang on. I don't want to lose you guys.
Because you don't have the extra O.
Right. Okay. Do you guys see what the problem is now? Here I don't have an OH. The two OHs have to be facing the same way to connect these. So I could connect these two, but I cannot connect these two. What was the difference? Yeah.
On the other one that you changed, it was 2 hydroxyl groups on the bottom. On this one, it's just a hydrogen and 1 hydroxyl group.
Okay. So I want you guys to look at this one. And this one. See the difference? Mm-hmm. Okay. The only difference between these two things was on the first carbon, right here by the oxygen. For the one on the left, the hydroxyl group is facing down, and for the one on the right, the hydroxyl group is facing up. These two are both glucose. However, this one with the hydroxyl group facing down, we call alpha glucose. And this one with the hydroxyl group facing up, we call beta glucose. And Zach, why does that matter? Which way it faces?
Because then you can't match them up next to each other.
You can't connect them, right? So it turns out that with the beta glucose here, now what if I did this? This is, by the way, this is another beta glucose. What if I did this? What if I took this molecule, guys, if you've had geometry, you go to the spatial thing, right? And I flipped it over. Can I take this whole thing and turn it the other direction? Ready, go. Now I have an OH here. The tail is facing down now, right? This becomes an oxygen. There. I flipped it over. Now can I connect it? Can I connect it now?
Mm-hmm.
Yes. Caitlin asked me.
Oh, I was just making sure the one on the left was alpha and then the one on the right was beta.
Alpha and beta, yeah. Okay, so guys, if you don't get anything else, listen to this point. If I have only alpha glucose, I can connect them sequentially, just together, because all the hydroxyl groups are facing down, so they're always together and it's fine. If I have beta glucose, every other one has to be flipped upside down so that they'll be together, right? And then the next one would be right side up, and the next one would be upside down. So it makes a difference. If it's a little fuzzy in your mind, think about this. If I want to make starch or glycogen, I can only use alpha glucose. If I want to make...
And you can put together two alpha glucoses.
Yes. You can keep, if you have only alpha glucose, this is always down, and the one on this side is also down. So it works. Every time it just works. Okay? But if I want to make cellulose, I would use beta glucose, and every other one would be upside down. So the structure is different. Why does that matter? Well, anybody ever ate grass before? Why don't we eat grass? We don't have an enzyme to break the bond between two beta glucoses. Okay, so this is not digestible by humans. We have the enzyme for the alpha glucose bonds. We don't have it for the beta glucose bonds. But it's good for us to eat plants. We eat plants, right? You guys eat tomatoes, lettuce, something like that, greens, whatever. They have cellulose in them. What does the doctor tell you that gives you? What do we call cellulose in our food? Because we don't digest it. But it gives our intestines substance to push when we're digesting. Fiber. That's what the doctor says. You need more fiber in your diet. They're saying you need more cellulose. Cellulose is dietary fiber. And we don't really digest it. We don't have the enzyme to break it down. But it gives our intestines substance. So when we're pushing the food through our body by this motion here, it's called peristalsis. It has something to push. If we don't have enough fiber in our diet, we can get stomach cramps and stuff from our intestines working too hard. Okay, I think we're back up and running here. So here is a picture of it. Guys, if I show you just the top row, you should be able to look at that and know it's starch, because you can tell by where the tail is of the cat, they're all facing up, that they're all facing the same direction. That would either be starch or glycogen, right? And then down here you can see that every other one is upside down, because every other one, this one the tail is up, and this one the tail and the head of the cat are down, and here they're up, and here they're down, so it's flipped. And the flipping is because of the direction of the hydroxyl group. Remember that? Questions on that? Everybody in the room is crystal clear? All right. Almost done. We're super, super close to being finished. Ribose has how many carbons? 5. Ribose is 5 carbon sugar. Both of these rings are ribose. Do you guys remember in 9th grade when you learned DNA and you learned deoxyribonucleic acid, right? DNA is made from deoxyribose, which is on the left, and RNA is made from ribose, which is on the right. And you can see the only difference is one is missing an oxygen, thus the deoxy. But that's not what this slide is even asking. This slide is asking what's the difference between ribose and glucose. First, the really obvious difference. Missing a carbon, right? It's a 5 carbon instead of a 6 carbon. Can you see the difference in the shape? Remember like the cat with the tail? And now here you have a house. Looks like a dog house. Okay. We already talked about starch. Here's what you need to know. Starch is energy storage for plants. Glycogen is energy storage for animals. And cellulose is for plant structure, cell walls. We already talked about all that stuff. On this slide, we don't digest it very well. We can call it fiber. It has long chains. Every other one is flipped. Those are only beta-glucoses. This whole slide is about cellulose. No new stuff there. Here's 2 pictures. We just looked at these a second ago. I should be able to show this to you, and you can tell me one starch and one cellulose based on the way the glucoses are facing. Within starch, there is something else that you need to realize, and that's that there are 2 kinds of alpha glucose links. Ready? One looks like this, where the line represents a whole chain of alpha glucoses. So imagine that that's like 100 alpha glucose molecules just linked together, and they kind of curl a little bit, right? And that's amylose. And amylopectin also starch is a chain of alpha glucoses, but it's really branched, kind of like a tree, right? You have main chain, and then you just have branches and branches and branches. So the difference between amylose and amylopectin is a lot more branched. Both of them are still only using alpha glucose. I know you don't have this slide. And I'll show you another picture. Not this one. I like this drawing because you can see the little six-sided figures. See all the little alpha glucoses? This is switched, so amylopectin's on the left here, and you can tell it's really branched. Then we have amylose on the right, and it's not that branched. If you're thinking, well, what about glycogen? Because glycogen's also made of alpha glucose. It looks similar, but glycogen is branched, but not as much as